right, welcome back. We're going to pick up with our next lesson. You've had an opportunity to dive in and explore some of these concepts with other instructional videos, and now I'm welcoming you back to kind of bring closure to our chapter. So we're looking at a closer look at solutes. We know that solutions are made up of two major components, solvents and solutes. So the solutes dissolve in the solvents. For example, salt and sugar both dissolve in water, but when they do so, they behave significantly different. Salt is an ionic compound, and you just practiced what ions mean, the loss or gain of electrons forming a positive or negative charge. We've learned that those are called strong electrolytes, that they conduct a chemical current, an electrical current, in solution. When ions form from compounds called salts, they are said to dissociate. The word dissociate means to simply separate into the ions the compound is built from. You must be a salt in order to dissociate and conduct an electrical current, as displayed in the videos that you have just watched. Now, sugar is a molecular compound. Sugar, of course, is made of all nonmetals covalently bound together, and when nonmetals bind together, they do so by covalent bonds, not ionic bonds, and therefore all nonmetals grouped together might be polar and dissolve in water, but they do not dissociate and therefore do not conduct an electrical current. And as our video lesson displayed, we have these chemical apparatus here to test conductivity. Here we have pure distilled water, no ions at all, so you see no bulb glowing, no electrical current. Same is true for the second category here, non-electrolytes. This is sugar water. Sugar water does form a homogeneous mixture, but does not dissociate into conducting ions. And finally, in the third picture, we are being shown a strong electrolyte, such as table salt, sodium chloride. We know sodium and chloride exist of ions, and ions conduct that electrical current that turn that bulb on, as displayed in our last video. So just highlighting a few of those lessons that you've practiced from the previous lesson, Na atom loses an electron to form a sodium ion. Chlorine atom gains an electron to form a chloride ion. We call this compound sodium chloride, that IDE ending on the negative ions. And you're asked to practice some of those examples in your sapling. If we have 25 protons, we know that's 25 positive charges, and only 21 negative electrons, what is the net charge on this ion? Well, we know that we need one negative to neutralize one positive, so we're ending with 4 extra positive charges. That 21 of the 25 positives have been neutralized, but I have a remainder of 4 that are not neutralized, giving this ion a +4 charge. We recognize the pattern on the periodic table, and if we've been practicing, we said on our chart we wrote +1 on top of all of those ions written here in our first group 1A column. They're all going to lose 1 electron. We wrote a +2 on the top of magnesium's column, knowing that they're going to form positive 2s. Aluminum a +3, zinc, cadmium, and silver we wrote in the box of our periodic table as well. And then these red ones are toned a little pinkish red. They know that they have a variable charge and must have a Roman numeral in their name to tell the reader what kind of charge they would have. So we would call, there we go, chromium Roman numeral 3. Chromium 3 ion is a +3. Chromium +6 is called chromium Roman numeral 6, and so forth. So some of these transition metals have a variable charge, and we simply let the reader know what charge it's carrying using that Roman numeral. And over here we know that fluoride's family carries a -1, oxide who carries a -2, as well as sulfide, and nitride with a -3. These noble gases in the last column here never form an ion. They're the envy of all of the elements on our chart. And so, again, another practice, just kind of thinking about charges. How many protons are in an ion with 36 electrons, so 36 negative charges, and the net charge is left as a -1? That means there must be a negative charge that's not being neutralized, and so that would give me 35 positive protons, leaving a remainder of 1 electron not being neutralized, so there's 35 positive protons. Same game here. How many total electrons are in the copper 2+ ion? How many total electrons? Well, for this one, I need the periodic table because I don't know the copper by heart, how many it starts with. Do you see copper on your periodic table? It is number 29. So an atom, a neutral atom of copper with its atomic number of 29 tells me that it starts with 29 protons, and because it's neutral, it would have 29 electrons as well. Alrighty, but now it's carrying a +2 charge, and so if it started with 29 protons and 29 electrons, that would have been a neutral atom, no charge remaining. Atoms are neutral. But now all of a sudden we have a +2 charge on the ion. Now remember, we can never ever change the positive protons. It's the number of electrons that change. And if I have a remainder of 2 that are not being neutralized, I now have 27 negative electrons, giving me a +2 overall charge. We've just determined the total electrons in a copper Roman numeral 2 ion to be 27, giving me that original 29 protons it started with, and we had to look that up using the periodic table. Classify each of the following. Are they anions or cations? Remember, cations are positively charged and anions are negatively charged. We know that metals will form positive ions and nonmetals will form negative ions. Positive ions are called cations. Negative ions are called anions. If we have more protons than electrons, we know that we would end up to be a more positive charge. And if they're negatively charged, we know that there's more electrons than protons. Group 7A and Group 2A. I'll just review where those are located here. Group 2A, the second column on our periodic table, all were positive 2s, and Group 7A, over here, fluorine's family, were all negatives. So as we kind of click and drag where that goes, I think I hit the wrong one. And we'll give the minute here to get back to our slide. Apologize. And we're just reviewing where the metals and nonmetals reside in that chart here. What we're able to do is to recall all the metals to the left are positive, and when you hop the border, all of the nonmetals to the right are negative. And so we can finish that sapling question while we wait for the program here to respond. We're simply looking at positive being a cation and the negative being the anion. And the last one that we're asked to just click and drag, we know that 7 is fluorine's family. They're negatively charged. And group 2A, we know that to be magnesium's family, and those are positively charged. Hope you can follow those arrows. All right, so now we know that metals and nonmetals react with one another to form ionic compounds. A potassium atom, we have to select an answer when the choices are gain or lose to form a positive or negative ion. Right off the bat, my friends, we know that the only thing that's ever changed from atoms to ions are electrons. We never touch the nucleus of the atom. It's always the electrons. Now a potassium atom, and again if I just hop back here quickly, potassium is a K+1. It's going to be a positive ion, and so it will be a +1 ion, and it's going to do that by losing an electron. And a sulfur atom, remember where sulfur lives, here's sulfur, it's carrying a -2. It has 2 extra negative electrons, so it's going to gain 2 electrons to form a -2 ion. So real helpful to just have that periodic table nearby. We'll capture those rules for naming ionic compounds. We've spent a great deal of time already in the previous video lessons that you've come back to this lesson from. So we know that positives and negatives form ionic compounds. We want to neutralize the charges to end up with a net zero compound overall. We simply say the name of the positive, say the name of the negative, and end with IDE. So lithium fluoride, calcium sulfide, iron 2 nitride. Hear how we're ending the IDE ending. You also have an opportunity to introduce yourselves to what are called polyatomic ions, groups of atoms acting as a unit carrying a charge. And so again, from our previous video lesson that you're coming back to this lesson from, we practiced at great length polyatomic ions: acetate, bicarbonate, carbonate, hydroxide, hypochlorite, nitrate, nitrite, phosphate, sulfate, sulfite, and here's our positive ion called ammonium. These carbonate and bicarbonate will play a significant role in our next chapter on acid-base rain. So we're practicing polyatomic ions, we're practicing ionic compounds with just a little bit of nomenclature. Nomenclature simply means how do I name and write formulas for ionic compounds. Magnesium oxide. Magnesium is the name of the metal. Oxide is the name of the nonmetal ending in IDE. Here we have sodium bromide, NaBr, sodium bromide. Notice that they are indeed electrically neutral compounds. And that's the goal, of course. When we start writing out our formulas, we need our periodic table handy. Lithium oxide, for example, I can find those charges right off the bat. Li is a +1, O is a -2. And so when we crisscross, we find our chemical formula, Li2O. Lithium, with its lithium with its +1 charge and oxide with its -2 charge gives me a compound called lithium oxide. And then oxide, O-X-I-D-E, oxide. Here we have calcium with its +2, sulfide with its -2, and remember where we're pulling those from. We're just simply looking at our periodic table. In the periodic table from this particular chart, here's calcium +2, sulfide -2. They are electrically balanced with a +2, -2, and so we just simply know that it would be called calcium sulfide. C-A-L-C-I-U-M for calcium. And then here's sulfur is the name of the element, but we're going to change the last name to the IDE, calcium sulfide. Mg3N2. Now remember, there's a little trick here that we can practice as we did in our previous notes. If we have Mg3N2, you know that those subscripts were used to electrically balance that chemical. So Mg must have been a +2. And see what we're doing? We're really just underlining this 2 here, making the magnesium a +2 and nitride a -3. Magnesium nitride. Here we have aluminum sulfide. Say the name of the positive, say the name of the negative, but it ends in IDE. So by uncrisscrossing, we come up with a little pattern to help us find the charges that were used when we, now I'm all over, when we were using our, oh my gosh. Sorry friends, let me just take a moment and clean this up. So I look like I've had just a moment of rage here or something. Magnesium nitride, Mg3N2, where we have Mg is a +2, N is a -3. And then of course aluminum sulfide. Aluminum came from the +3, sulfide came from a -2. The magnitude of the charge, we have +3 and a -2. Aluminum sulfide. And again, magnesium must have been the +2. And nitride must have been the -3 by uncrisscrossing magnesium nitride. Or, just a nice good reminder, we can look up the charges, magnesium nitride, right off of the helpful periodic table. And you're going to see many of these examples in your homework assignment. Let's write the formula for potassium sulfide. Potassium sulfide. K with its +1, sulfide with its -2. So when we want to write a formula for potassium sulfide, K plus, S -2, we notice that it's not electrically balanced just yet, but we're going to use that crisscross method. It takes 2 units of the +1 to electrically balance 1 unit of the -2. Our chemical formula, K2S, potassium sulfide. Name the following. Well, here I have a group of atoms acting as a unit carrying a charge. We called that a polyatomic ion. You're not really expected to memorize, but you should be, should know where to find the name. PO4 -3 is called phosphate. Hear that ATE ending? Phosphate. So we would know that is called the phosphate ion. Here the ite and the ate, nitrite, nitrate. And I can look those formulas up right here on the polyatomic ion chart. Here's my nitrate, NO3 with a -1 charge. Here's the nitrite, NO2 with a -1 charge. So a very handy tool page, the polyatomic ion chart. And the last one it says is cyanide. CN -1 is called cyanide. So polyatomic ion chart. In our next example, we're practicing our nomenclature. Here we have sodium sulfite. Here the ITE. So we have 2 tool pages to use. We need the periodic table for the positive sodium, Na+, and we'll need the polyatomic table to find the last name, sulfite. Sulfite is SO3 and it carries a -2 charge. So sodium sulfite, looking at both examples, we would have sodium with its +1. So I would have Na carrying a +1 charge. And the polyatomic ion sulfite is SO3, and that entire species carries a -2 charge. And so we'll crisscross our charges and come up with our subscripts, SO3 -2 here. So we crisscross and we get Na2SO3, sodium sulfite. Potassium with its +1 charge, and the polyatomic ion called phosphate with its -3 charge. Again, it's not yet electrically balanced, but we know how to crisscross, and we get K3PO4. With your silver, which is +1, and sulfate, find it on your polyatomic. See it there? SO4, -2. We crisscross to balance the electrical charge. 2 units of the +1 electrically balance 1 unit of the -2. Remember, ammonium is our positive polyatomic ion. Ammonium is NH4 and carries a +1 charge. Nitrate, here the ATE, we know it is polyatomic as well. Ammonium is +1, nitrate is -1, electrically balanced already to be 0, so we get ammonium nitrate, NH4NO3. Lots of practices, and we're getting the hang of it. The more we do, the easier it becomes. In our next example, we have the same idea, writing for more ternary ionic compounds. We have polyatomic ions, and I won't do them all, but just remembering that we simply write out the positive, Na, sodium, look up its charge, we know it's a +1. The ATE ending tells me it's polyatomic. Perchlorate, ClO4, carries a -1. +1 -1 is electrically balanced, so I'm done with NaClO4. Potassium permanganate, calcium sulfite, lithium cyanide. You'll find the metals on the periodic table. You'll find the last names on the polyatomic chart, and make sure you consider charges when writing out their formulas. Many of these in a row, and I'm just going to kind of scan through and see if there's anything that we're missing that might look different from the practices we're looking at. So again, same idea. Here's one, calcium and nitrate. If calcium is a +2, find it on your periodic table, second column, and now the polyatomic ion nitrate is a -1. This is not electrically balanced, but we need to take 2 groups of the negative ion, and this is where we practiced in our other video together. We bring in a parenthesis, bring that 2 around and down to take 2 units of the polyatomic ion known as calcium nitrate. CaNO3 taken twice. Here we see the Roman numerals telling us the charge to use on the ion. Since copper lives in the heartland, if I don't know your charge by where you live, I'm now telling you the charge with that Roman numeral. Copper Roman numeral 1 tells me to use copper +1, and here's bromide, which is a -1. Copper 1 bromide, CuBr. But copper 2 bromide tells you to put a +2 on the copper, and so this time when we neutralize, we'll have to crisscross and make that CuBr2. Copper 2 bromide. And so we begin. We have iron 3 bromide and lead 4 bromide. Bromide is always the -1 charge. The Roman numeral tells you what charge to place on the metallic ion, and just simply crisscross to neutralize the charge. Over here we're looking at oxide as the last name. Oxide we know to be -2. If we have copper 1 oxide, we're going to hook copper with its +1 charge. So therefore, when we crisscross, we get Cu2O, copper 1 oxide, Cu2O. If we have copper 2 oxide, the copper with a +2 electrically balances the -2, and you just have CuO, copper 2 oxide. And this one is kind of a little unique. Well, here's lead with a +4 based on its Roman numeral telling me it's a +4, an oxide with its -2. The most common mistake here when we crisscross, we get Pb2O4, but remember that can be reduced and must be reduced to the lowest subscript ratio possible. It only takes 2 oxides to electrically balance 1 lead. So instead of a 2 to 4, we'll write that as a 1 to 2. It's still named lead 4 oxide. And again, many practices, and I am just giving you an awareness that the nomenclature series that you're coming back from is critically important to be able to do your sampling. And you see many opportunities to practice those skills. So if you need to go back and kind of keep practicing with the previous lesson on ionic compounds, please do so. And I must also stress the electrolyte compound, because the electrolytes, as they dissociate in water, they're going to play a role not only in this particular chapter, but in the next one as well, when we talk about acids and bases in terms of ocean acidification. To be an electrolyte tells me that the salt dissociates, that it breaks apart into aqueous ions that are a great conductor of current. And you had an opportunity to actually watch an animation of that particular concept. So remember, the way that the water actually brings these ions into solution, oxygen is a little bit negative, and you're going to see that the oxygens are going to completely surround the positive ions. And if you see the hydrogens, which we know to be a little bit positive in terms of polarity, those positive hydrogens are going to completely surround the negative ion of chloride. And you'll start to see that dissociation where the positives and negatives arrange themselves based on electrostatic attraction. This process is called solvation. Many ionic compounds will dissociate. If we have a compound called sodium, who carries a +1, and the polyatomic ion called sulfate, who carries a -2, Na2SO4 is our solid salt called sodium sulfate. When this dissociates, when it breaks apart into its ions by being dissolved into water, we would release 2 units of our sodium ion, aqueous, and the polyatomic ion called sulfate, SO4, who happens to carry the -2 charge. So the salt as a solid dissociates into the ions it's built from. 2 aqueous ions of sulfate. Remember, sulfate is 1 unit, 1 polyatomic ion acting as a unit carrying a charge of a -2. So even if there's a whole lot of letters, there's still only 2 ions there. So we have ammonium nitrate, whose chemical formula is NH4NO3. Ammonium is a polyatomic ion. It carries a +1 charge. Nitrate is a polyatomic ion. It carries a -1 charge. And when it dissociates or separates into its ions, we release the positive polyatomic called ammonium and the negative NO3 negative, which carries a -1. Ammonium nitrate, starting with the solid, it dissociates into its aqueous ions and is a strong electrolyte. So even though there's lots of different letters, remember there's just always 2 ions it's built, the positive and the negative. Ionic compounds tend to be water soluble. However, there are some salts that are insoluble in water, such as silver chloride. Silver chloride is not an electrolyte. It does not dissolve in water. In other words, the attraction between the silver ion and the chloride ion is a greater attraction, greater electrostatic attraction than it has towards the water molecule, and therefore remains intact and does not dissolve. Mercury chloride, barium sulfate, these are all insoluble salts that the intermolecular attraction for the ions is greater and therefore stays together. Carbonates tend to be water insoluble, no matter what their first name is. It has to have a positive name here, but carbonate as a last name tends to be insoluble. And hydroxide, a polyatomic ion, also tend to be insoluble. Our text provides us a solubility table, and the solubility table helps us predict if the salt will be soluble, which means to dissolve, or insoluble, which means it will not dissolve. So for instance, sodium, potassium, and ammonium, ammonium is our positive polyatomic ion, NH4+, are always soluble. No exceptions. So sodium nitrate, potassium bromide, because their first name comes from those first family elements, sodium, lithium, potassium, rubidium, and the positive polyatomic ammonium, always soluble. If your last name is nitrate, you're always soluble. Chlorides tend to be soluble except silver, mercury, and lead. Sulfates except for strontium, barium, and lead. Carbonates insoluble unless you're hooked to one of these first family names, sodium, lithium, potassium, and so forth. And hydroxides unless you're hooked to a first family name, because first family names are always soluble. So a little general rule of helping you predict if something is soluble or insoluble in water. Here we have nitrate. Nitrates are always soluble. Barium sulfate. Remember that was a rule breaker, barium sulfate? Right here it says barium sulfate is insoluble. That rule right there is going to help us predict that barium sulfate does not dissolve in water. Here's another nitrate as well as potassium. Two rules right there help us predict. Potassiums are always soluble. Nitrates are always soluble. So both of those rules help me predict, yep, you're going to dissolve in water. How about iron carbonate? Iron carbonate. Well, look at carbonates are insoluble unless you're first family metal, but iron is not. Iron is a transition metal, so it's not going to dissolve. How about copper chloride? Chlorides are soluble unless it's silver or mercury, and I'm even going to include this for you. Add this onto your chart. Lead chloride is not soluble either. It's a heavy metal chloride. It will not dissolve. So this is something interesting as well. This is a mistake in your table. It's supposed to be mercury's symbol, and they accidentally wrote magnesium. Well, I see what they did. Sorry. Magnesium chloride is soluble. Silver chloride is insoluble. All right, so that's fine the way it's written, because this is an example of its solubility. Silver, mercury, and lead are all insoluble if their last name is chloride. So silver, mercury, and lead are the chloride exceptions, and we'll add that on there. And that's going to help me predict this guy. Lead chloride is insoluble, and copper chloride would be soluble. So heavy metals such as silver, mercury, and lead are insoluble. Copper chloride would be soluble. And just practice using that solubility table to gain insight there. And as you're wrapping up your chapter on our water quality, environmental consequences, you'll read about nitrates and heavy metals that are getting into our water systems. Again, practice here with the water solubility. Your sapling will actually be able to pull up a solubility table that's much more complete and just go by the last names. Potassium here and bromide. Potassium is a first family metal, always soluble. Here, if you pull up your solubility table, you'd see that zinc phosphate. Phosphates tend to be insoluble, and so forth. And I won't do all of these for you because I want you to practice using the solubility table. It's a table that helps us predict if something will dissolve in water or remain as a solid, as an insoluble salt. And just glancing through anything else as we bring closure to the lesson. For each of the solutes, identify the better solvent, water, or carbon tetrachloride. And this goes back to our lesson of likes dissolve likes. Likes dissolve likes. Water is a polar molecule. And when I just think about what that means, I understand water, HOH, is going to have regions that are negative with those exposed electrons, and we drew that as a partial negative, and it's going to have a region that's partially positive down here on the hydrogens. Water is said to be polar. Polar substances will dissolve anything that also has a charge, any kind of polarity, likes dissolve likes. Carbon tetrachloride is a completely symmetrical molecule. Carbon tetrachloride, if I stand in the center atom, I stand here, I look up, down, left, right at all four domains, they're all identical. This is said to be a non-polar molecule. Likes dissolve likes, so anything that is non-polar is going to dissolve better in carbon tetrachloride. If ammonia is written out as its Lewis dot structure, NH3, you see these exposed electrons on the nitrogen? This is a polar molecule due to that exposed electron set up here, making this region a little bit negative. Ammonia will dissolve better in a polar solvent than a non-polar solvent. C6H6 is called benzene, and benzene is a perfectly symmetrical six-sided molecule, C6H6, where we have a cyclic structure, and that cyclic structure places a hydrogen around each of the carbons. So all 6 hydrogens attached to the carbon. Notice how we're ending up with just a completely symmetrical molecule. And knowing that carbon needs 4 valence bonds, benzene would show an alternating double bond, single bond, double bond, single bond, double bond, single bond. This is a very important industrial chemical called benzene. And I drew it for you simply because you're now seeing that it's a perfectly symmetrical molecule. It is going to be nonpolar and dissolve best in the nonpolar solvent, carbon tetrachloride. Your next compound, potassium fluoride. Do you notice this is built of ions? Potassium's a +1, fluoride is a -1. It is a water-soluble salt and would dissolve very well in the polar solvent based on its oppositely charged ions. And the last one is iodine. Iodine, in the molecular form, is just 2 iodines bound together with a single covalent bond. I single bond I is the molecular iodine formula. Of course, this is a non-polar molecule, perfectly symmetrical. The electron density is very equivalent all throughout that molecule and would likely dissolve in the non-polar solvent, carbon tetrachloride. Likes dissolve likes is a review here from our lesson on solubility. Rank these compounds by their expected solubility in hexane. Now hexane, hear that hex? That tells me that there's 6 carbons all in a straight branch. That's a C. 1, 2, 3, 4, 5, 6 carbons, and the 14 hydrogens just make a straight alkane chain, 6 carbons in a row. So reason I'm drawing this is to clearly show that this is a non-polar solvent, non-polar. So here we have the first structure called ethanol, CH3, CH2OH, CH3, CH2OH. Clearly you see this is a polar molecule, but it has a little non-polar chain as well. The next one is C2H6, which is just straight carbon chain, C2H6. And then we have the water molecule, HOH. Who is the most polar? Who is the most nonpolar? Knowing that our solvent is nonpolar, the most soluble in the nonpolar would be this guy, the most nonpolar molecule. C2H6 has nothing in it that would lend itself to not dissolve here. So likes dissolve likes, we're looking for a nonpolar. The least likely to dissolve is the most polar substance, water. And the guy in the middle here, because it has qualities of both, it has a polar region, but it also has this nonpolar region. We're going to put him in the middle. So we'd say C2H5OH would be in the middle. So most soluble to least soluble. Most nonpolar to most polar molecule. And I think we're going to wrap up our lessons very soon here, and you're going to finish off your reading and your video lessons on water filtration and contamination of the water systems with our video lessons. But I wanted to just kind of bring closure to the actual sapling examples found in your homework with this last video lesson. So great work on your Chapter 5. You're ready to tackle sapling, and consider submitting some of your outlines and video notes and tackling your test. Great work today.